My name is David Hyde. I've been a frequent visitor to the San Juan Islands for almost a decade now, and I am now a summer resident of the islands. I've been introduced to the controversy surrounding the CAO and SMP development over the last 2 years, and with my oceanographic background, which I'll mention here in a moment, decided to dig into the scientific literature for the local area, the waters surrounding the San Juan Islands. I'm retired from a 38-year background in ocean sciences and technology development, working both for the military and for the hydrographic community, and have been involved in a lot of programs over the years for major undersea installations, including scientific data collection installations. I had a 4 or 5 year residency at Scripps Oceanographic Institute on several major projects, and have been a close associate of Dr. Walter Monk, who's probably the leading U.S. oceanographer, the Dean of Oceanography, Physical Oceanography in the United States during the 1990s. With that background in mind, when I looked at the best available science that as it then was accounted for as of late last summer in September, I saw a preponderance of environmental studies in the Puget Sound involving sedimentation, water quality, and so forth. And but I didn't see much, if anything, involving the San Juan Islands themselves and the regional waters around the San Juan Islands. And with that in mind, I did a literature search and found a very rich body of literature, mostly Canadian, from the Institution of Ocean Sciences in Sydney, over in the Saanich Peninsula, that details all of the characteristics, physical oceanography, water circulation, chemistry, sedimentation, sediment transport, and so forth, from the Straits of Juan de Fuca north through the Haro Straits and involving the San Juan Channel, and up through Boundary Pass and into the southern Straits of Georgia. So with that in mind, the purpose of this presentation is to give everyone a summary of what is known about the ocean characteristics in and around our islands. And and as you will see, we are in a rather unique situation here, which is not very coupled to the Puget Sound situation at all. It's much more closely allied with the Canadian waters. With that in mind, we'll begin. So the title of the briefing is Ocean Circulation, Sedimentation, and Chemistry, for that matter, in the San Juan Island archipelago. This archipelago is that small center archipelago in the middle of a very large Salish Sea system, which has 3 principal estuaries. Now remember, the definition of an estuary is a body of water, an inlet, which has a freshwater flow into it from a river system and is mixing with ocean waters and is mixed during tidal cycles. And that indeed is the case here in both the southern Puget Sound side and the northern Straits of Georgia side. The Straits of Georgia tend to be on the order of 20 to 25 miles wide, and with water depths between 600 and 1,200 feet. The Puget Sound is 10 to 15 miles wide at its widest, 5 miles, and is 100 to 300 feet deep. And indeed, the Straits of Georgia system is on the order of 10 times the volume of the Puget Sound waters. They are coupled through the Straits of Juan de Fuca to the open Pacific, so the water flow from the freshwater outlets flows out through the Straits of Juan de Fuca from both sources. So tides, currents, river outflows, and bottom water mixing are major factors in and around our islands, and they frankly overwhelm any local runoff water quality issues. So the briefing will explore basically water quality, sediments, and local impacts. I'm going to also mention some longer-term trends toward the end of the briefing, because everyone wants to know whether the water is getting warmer and what will be happening with rainfall in that area. And there is an assessment of the next decade or two in that matter. This is not a climate briefing, however. There's a very rich body of scientific literature that's been uncovered here. There's 50 to 75 peer-reviewed scientific papers in major oceanographic journals that comprise the main body of it. And they do have an impact on the best available science that should be under consideration by San Juan County for both the CAO and the SMP. So, bottom line assessment. This is the conclusions from the data that I'm about to present. That the San Juan Islands archipelago is 98% in the path of a massive circulation system, which is dominated by the Fraser River and its brothers and cousins, that are pushing a mountain of fresh water out to the ocean on an annual basis that peaks seasonally between May and August of each year. And that all of the water quality issues that we have, being 98% in the path of this circulation system, are basically as the effects of 3.5 to 3.7 million people, Canadians. Given that, almost no measure being taken by the San Juan County to mitigate perceived local runoff problems will have, on a general scale, will have any effect whatsoever on the marine shoreline water quality. There's too much water moving too fast in and out of these islands all the time. Only the Canadians can fix general wide area water quality issues within our coastal waters. The data we have on the water quality that exists around the island shows that it's generally pretty good. The Canadians have made some progress with regard to the city of Victoria and 20 years of improvements in the Fraser River watershed, and they're continuing to make improvements. Nothing that is going on, alternatively, in the Puget Sound affects the San Juan archipelago. Those waters flush down toward the south, and they don't mix. So they don't affect the San Juan archipelago, nor are they affected by any of our environmental measures. So any studies linking Puget Sound issues with the San Juan County issues are frankly inaccurate. The county's environmental initiatives for its coastal zones can only make a difference on a few local issues that it has, generally localized upper bays with reduced flushing. The main body of shoreline and all through our islands are very, very well flushed. Some of the best flushed in the lower 48 states. So considering the nature and the tested oceanographic science that connect our archipelago and our coastal waters to the Canadian circulation, there frankly can be no measurable change in the overall San Juan County water quality from the current CAO or SMP initiatives, and a focus on spot issues would instead be far more productive. Having said that, when we went into this literature search, we asked the questions, and the picture here with all these color bars is the population density of the entire watershed of the region. You have 3.5 million Canadians up here, 3.5 million U.S. citizens down here. But 8 times as much water coming down this direction as is coming that direction.
Interesting.
The connection with the Puget Sound is frankly a political connection. It is not an ocean circulation connection at all. In terms of the current state of the physical oceanography, there has been 30 or 40 years of good work that has been done by local universities, including the University of Washington, the University of Victoria, British Columbia University. And a lot of this work has been concentrated at the Institute for Ocean Sciences, which operates all of the Canadian research vessels as well as hydrographic vessels that ply the western waters here. In that, and from that, we have to ask the question, can a big picture, can an environmental baseline for these islands be be specified, quantified, or measured? And I think the answer to that is, based on the literature that exists, the answer is yes. And frankly, are there any specific shorelines within the county where county actions might make a difference? And I think the answer to that is also yes, in a few cases. Okay, how do water and other things move around in the strait? This is a cartoon which brings in the effects of the winds, the solar energy, winds and storms, along a line down the center of the Strait of Georgia, through the Boundary Pass, and around the Haro Strait, and out through to the Pacific Ocean. It's called a transect, and that line is about 600 kilometers long. With the mountain of fresh water that has moved through, and our islands are right in this little section right here. With the mountain of fresh water that's moved from the southern Straits of Georgia out into the Pacific Ocean, an upwelling bottom current, a countercurrent, is actually created. So there's a lot of fresh water moving out on the surface, called freshwater export, and there's an upwelling bottom water that's brought up to the islands from the deep Pacific Ocean. And it's that bottom water that we see upwelling along our coastlines. We are in a very active tidal mixing zone within the islands, and that has a major impact on how sediments move, how they're mixed and remixed, and where the sediments in our beaches come from. All of this has been incorporated into oceanographic circulation models that can make predictive predictions about chemistry and currents and all the other features that we are generally interested in. Okay, this is the same cartoon suggesting in the nutrient cycle, in the geochemistry cycle. The upwelling brings water of a different pH, acidity. It brings water of a different oxygen content. It's oxygen-rich water. It brings water that has nitrates and phosphates in it, up from the Pacific Ocean. And this is from all the deep sediments in the Pacific Ocean. As you go down toward on the continental slope in the Pacific, those waters are rich in nutrients from all of the debris and all of the stuff that falls through the ocean. And so this is nutrient-rich water that's being brought up here. There are atmospheric contaminants from ships, from airplanes, from cars, from civilization in general that are entrained on the surface. And then there's all of the runoff issues with the major river systems that are bringing what's basically organic carbon particulates and nutrients into the surface waters. And so all of this, and then the ultraviolet from the rays from the sun are actually converting some of this stuff into different stuff. So there's a rain of particles that are being deposited throughout this system that are being brought in by upwelling and that are being redeposited on the bottom. Okay, ocean currents. Is there estuarine mixing in the Straits of Juan de Fuca? And the answer is very little. These are flow lines, and this is 1 meter per second. So these are 1 to 2 to 3 meters per second. That's several, 2 to 4 knots of current during a peak tidal flow, and they show you the flow lines of the current coming in on a flood tide coming up into the Haro Strait. And this is the city of Victoria right here, and this is Port Angeles down here, and whatever it is, Spit down there. And what you see is that a highway of water flow going north and then going south. And here it comes out on the tidal cycles, on the ebb tide cycle, coming out of the Haro Strait and flowing out the northern side of the JDF, and bottom water, and the waters from the Puget Sound flowing out on the Puget Sound side. You do not see north-south water flow. The eastern Straits of Juan de Fuca are blocked bathymetrically by the shallow islands, Smith Island and the archipelagos around it, and So everything keeps pretty much to their side of the highway. And we are on the northern side. That's the Canadian side. Okay, these are very, very high energy tidal cycles. We have 2 to 4 knots that can erupt in the Straits of Georgia and in the southern part of San Juan Channel. I just went through one yesterday that was that registered 5.5 knots peak in there. It was a real mess getting through it, and that magnitude of tidal flow creates an enormous amount of vertical turbulence. So there is vertical mixing throughout the water column, extending from the bottom to the top of the water column in most of these channels during the high energy tidal flows. This tidal flow, of course, is a daily occurrence, and it overlays the northern river outflows. So there's a net southern flow from the river. The fact that the rivers are flowing in at very high rates, and the Fraser River peaks out at more than 10,000 cubic meters per second of river outflow. And then the tidal cycles are sloshing back and forth on top of that. Okay, these tidal cycles actually form vortices, big eddies that propagate across the Haro Strait, and these are very accurate tidal flow models that are published by the Institute for Ocean Sciences, and they represent a very mature ocean circulation model which coincidentally happens to include our islands, because we're sitting between 2 Canadian ocean regions. And so here you're seeing stream flows that are on the order of 3 to 4 meters per second. I mentioned about the vertical mixing in the Haro Strait. This is a very colorful little chart from one of their papers, which shows vertical velocity at the bottom, temperature gradations, and then the backscatter from the echo sounder that was used to make the measurements. The black areas, dark blue areas here, are downwelling with a velocity of up to 40 centimeters per second. That's basically half a meter per second. That's about 1 knot going down, and then the red areas are about 1 knot going up. And then when you see the big boils out there in the Haro Strait and the San Juan Channel, as what you're seeing is the effect of these vertical circulation eddies. To the north of us, these are the southern Gulf Islands, Eterna Island, and so forth. Coming out of Boundary Pass, you see a very high low rate coming in and going out, and then it immediately dissipates into a very, very calm and uniform flow field in the southern Straits of Georgia, by dint of the very mass of the straits themselves. There's a huge amount of water there.
See,
so the streamlines that you're seeing are...
This is flood and this is ebb, is that correct?
This is flood coming in.
Okay.
And this is ebb going out.
Okay, I just wanted to...
Okay. So this is Susha Island, for instance, here.
Yep.
You'll see a little bit of water that comes down the Rosario Straits, but it's frankly a tenth of the water mass that goes through the western sides of the islands. Okay, where does all the fresh water come from? It comes from the Fraser River and the Fraser River complex, and which happens to be the watershed for about 80% of the population of British Columbia. There are other British Columbian rivers that add to it. This last year, during June to September time frame, is charted here with actual outflow measurements of the Fraser River. It ran at about 9,000 cubic meters per second from early May until about the middle of August. That produces about 25% of the total water mass of the whole southern Straits of Georgia. So you have to envision a mountain of fresh water building up that has to have an outlet, and the outlet is mainly to the south. 10 to 15% of it can go north through the Johnson Strait, but those are very, very restricted passages compared to what flows out through the San Juan Islands. That generates a current, a southerly current, net current of between 4/10 and 8/10 of a knot average flow outwards. The surface plume in this from the Fraser River, which many boaters have seen, it's a pretty brown water up there, is mixed by tidal action, which is relatively benign in the southern Straits of Georgia and starts to provide that turbulent mixing at the beginning of Boundary Pass as it comes down into the Straits of Georgia. And I will show you some satellite photography that shows what that sedimentation plume looks like. There's 30 million metric tons of annual particulate outflow from the Fraser River, 2/3 of which is suspended in fine sediments. The coarse sediments are deposited into the Fraser River delta fan, and they're sloshed back and forth by tidal actions, both to the north and south there. But the fine suspended sediments tend to stay in the water column much longer and are actually deposited in our waters, as you will see. It's a very complex process, but the local mixing to the next slide. Okay, now stream flow and nutrients from the San Juan Island streams and creeks, if you want to call them that, have been measured. The last one, set of measurements I could find was in the year 2000, where they did a monthly survey of 31 different stream beds in the San Juan Islands. And this is a composite of the results from that survey by month. So this is March 1999 through February of 2000. And this bar graph shows you the flow rates in 10 and 20 cubic feet per second of all of those streams put together. So it's a rather low rate. And in fact, in the summer months, it's of course none. And then in December and January, you'll see a measurable increase because of the rainfall. The second chart shows you the measured nitrate concentration in parts per million, where an acceptable level is around 1,000. And you'll see that these streams do contain some nitrate concentrations, but all within the acceptable range. And the nitrate concentrations in the offshore waters are in this range also, but they are not. That is not nitrate from the islands. That's nitrate from the bottom waters of the Pacific Ocean, from the upwelling. Okay, satellite mapping of suspended sediments. They are NOAA and NASA have a series of satellites, Earth observation satellites, that have special optical instruments on board that can measure in very narrow spectral bands. They can measure the existence of both chlorophyll and fine-grained sediments in near-surface waters of the ocean. And this is a great synaptic mapping instrument. In this color coding scheme, white is a very high concentration, and blue or black is either no data or no concentration whatsoever, perfectly clear water. So here are two charts from 2001 in July, showing on the left the plume from the Fraser River in terms of a sediment concentration coming down to Boundary Pass here, and then being mixed up through the tidal turbulence in this water. And of course, the Fraser River complex extends way up into here, but this is the Fraser River Delta right in there. And so you'll see this and the net effect of this southerly flow. Chlorophyll concentrations, you'll see chlorophyll offshore, again due to the nutrients from the upwelling in the western Pacific. A good deal of nutrients in the southern Straits of Georgia that's associated with this plume, and those nutrients flow down are flowing down through the islands. So both sedimentation and nutrients are an area where it's a very complex process in terms of circulation and mixing, and the sources are largely external to the islands, not internal. Okay, sediment suspension and remixing in the channels. Here are actual measurements of the sediment density on a vertical scale on that same transect through the islands, where this is the Pacific Ocean out here, these are the San Juan Islands in here, and a whole series of acoustic measurements were made that can actually measure particle backscatter and hence particle density. And this is the southern Straits of Georgia, and this is the freshwater plume at the surface from the southern Straits of Georgia. And this is June, July, and September. The highest concentration of sediments you see down toward the bottom and through this transect. Boundary Pass, down the Harrow Strait, over the Victoria Sill here. And so this turbulent tidal mixing is carrying on all the time. It's actually picking sediment up off the bottom during some tidal cycles and then redepositing it elsewhere. And I'll show you some pictures that have been made of very high resolution bottom mapping by the Moss Landing people in this. And in September it continues. This actually continues throughout the year. So the sediments that are down there are being picked up, they're being transported, and they're being plunked down someplace else. This is one of the Moss Landing very high resolution bottom, it's called slope shade bathymetry. This is actually acoustic multi-beam survey, but it's of such high resolution that it's almost like an optical survey. Yeah. So you can see the geological features of the bottom, where and the survey area ended near the shoreline here. But this is Saturna Island right here, and this is the so-called Boundary Pass Sill, where the water gets up to only 300 feet deep instead of whatever. And you'll see mounds of sediment build up on each side of this, where, depending on whether it's a flood tide cycle or an ebb tide cycle, stuff is being poured over the sill and deposited. You'll also see one of the largest areas of moving underwater sediment dunes that's ever been measured, right in the Boundary Pass here. These are moving sand waves, or mud waves, sediment waves, that are moving around, that are being pushed by the tidal currents in that area. And this is one of the sources of sedimentation that's being pulled up into the water column and then redeposited sometimes on our beaches. And you'll see other areas of, and then you see these rock outcroppings, and so you see the basement rock for the islands themselves. This is the southern part, and this is another very large area of moving sediment dunes. And these are 50 to 75, 80 feet high, sort of dune structures. And then over towards Lopez Island you see the sedimentation there, and then up the scour, and you see rock outcroppings everywhere that are creating the highly turbulent flow through these channels here. So they've done bottom cores as part of this survey. This was a survey done in 2002 and 2003 by the Institute for Ocean Sciences using their ship, and the Moss Landing's Oceanographic Institute down in California. And they've created a very large database in and around the islands that show the sediment characteristics. The only thing to take away from this is the pink area are what are called sediment waves. So these are all moving, all of this pink stuff is areas of moving sediment that's being pushed around tidally. The blue areas are pre-tertiary basement rock, and the red areas are bedrock in all of this outcroppings. So what do these seabed maps actually tell us? The tides are remixing bottom sediments. The sediments are settling in quieter waters, as they do during the quieter periods. And we have a constant exchange and influx of sediments via this tidal exchange process in virtually all of our bays and harbors, with the exception of one or two of the interior harbors that are pretty well isolated from it, like the upper part of East Sound. This plume of sedimentation that comes from the Fraser River lasts between April and August every year. So there's a major influx of sediment on about a semi-annual basis.
Makes sense.
The remixing part of it spans all of the seasons. So from a sedimentation standpoint, we're in the middle of a very complex process. Okay, let me switch to the regional long-term trends. The Canadians have been making measurements at fixed sites, Entrance Island, south of Nanaimo, there since 1938 on an annual basis. And they have instruments since 1970 that have been measuring the temperature in the water column. And so there's some long-term trend data for the temperatures of our waters over in the last 7 years in the case of Entrance Island. And you see a cyclical, several cycles of trend, and the suggestion of an increase in temperature of about 0.15 degrees centigrade per year, about 0.3 of a degree Fahrenheit per year. That's a suggestion because there are Pacific Ocean decadal cycles that can stretch for 50 to 80 years. Not just the El Nino and La Nina, but others on top of that. So it's very difficult to tell whether this is a long-term trend or not. And from a color-coded standpoint, you see a lot more bluish down in the earlier years here in the water column than you've seen in since the year 2000. These are data again from the Institute for Ocean Sciences. This is in the southern Straits of Georgia, by the way. Okay. Back to summary finding and conclusions. The local tides here are very energetic. They do create turbulent mixing throughout the islands, shoreline processes, the marine zones. They're constantly bringing up bottom water, and hence the low temperatures in the islands. We don't have beaches here with 70-degree water in them like they do up in the northern part of British Columbia. Everything is mixed here. This is actually a good thing. The salty bottom water is the really clean stuff, despite the low but average nutrient load that it brings. The San Juan Archipelago, frankly, has the best flushed coastal waters anywhere in the 48 states. Maybe a few spots on the Maine coast have, but the currents here and the turbulence here and the Pacific bottom water being brought in through the Straits of Juan de Fuca are major additions to the flushing process here. Oceanographers measure the resident time of water as a measure of how long a specific mass of water stays around. In the lower Puget Sound, that time is 30 to 60 days that it takes for the water to dissipate, dilute if you want. In the San Juan Islands, it's between half a day and 2 days. So the residence time of water here is very, very low. There are several partial local exceptions. The northern reaches of Orcas Islands, East Sound, and to a very limited extent West Sound, are more subject to runoff and reduced flushing issues than other parts of the islands. They have a higher residence time there because the water isn't moved out quite as fast. Friday Harbor here locally has relatively high density of urban runoff, streets, tires, oil, but it has excellent flushing in the harbor. And unfortunately, it still has to periodically chlorinate its wastewater treatment plant effluent because its UV system is breaking down. And that's not good. But other than that, we're in very good shape in these islands by anybody's standards. So above issues aside, the coastal zone runoff to the ocean is very rapidly transported to the Straits of Juan de Fuca and hence to the Pacific Ocean. And this body of information, frankly, does not support the imposition of any extraordinary restrictions on buffer zones, buffer zone extensions, as appear to be being proposed in the current CAO and SMP developments. So what can you take away from all of this? We're in the I'm saying it again, we're sitting in a unique marine setting, very high energy tidal flows. We're exchanging Juan de Fuca bottom waters and seasonally freshwater plumes with the southern Straits of Georgia constantly. We have access to a world-class resource in the Institute for Ocean Sciences for both tidal flow modeling, chemical oceanography, physical oceanography, and everything else we need to know about the waters around our islands. The refreshes the waters and renews the nutrients that are in the water around our islands all year round. And the renewal time of these waters is very, very short. As I mentioned, half a day to 2 days. And most bays and harbors exchange a very high percentage of their volume with the channel waters daily. And frankly, our sedimentation processes are, again, dominated by the Fraser River plumes in all of that. It's bringing it in, it's depositing it in our channels, and it's being mixed and brought up on our beaches by the tidal action in the channels. We're very slowly warming in the, according to the whatever we can measure in the trends. And frankly, that warming trend is creating a precipitation increase to the north of us, which is going to bring higher net average Fraser River flows annually in the future than it has in the past. So 50 years from now, there's a multi-decadal prediction of a 10 to 25% increase in precipitation and runoff. With the warmer winter cycles and the freshwater outflow from the southern Straits of Georgia will become more uniform during the year and less peaked on a seasonal basis because of the snowmelt. There is a compelling and extensive scientific literature to back all this up, and that literature is there available to set a baseline for the San Juan Islands environmental updates if the county chooses to use it. Thank you.
You bet. That's what we've been saying.